Welcome back to our series on the FFT. This is our fourth installment in the series, and today we're going to have a lot of fun. This builds on everything that we've worked on in the previous three series, so if you haven't caught up on those, you can always go back and catch them on the website. Today we're going to build a Max for Live device that's going to implement an effect using FFTs. The effect we're going to implement is going to be a multi-band delay, where each band of the FFT can be delayed by a different amount with a different amount of feedback, and you can create all kinds of really super fun effects with that. First, since we're doing a Max for Live device, I've created a new live session here, and then I'm going to drop in some audio to test our effect with. I'm just going to use this Jazz Brushes clip. It'll work fine for our purposes today. We'll just listen to it. Okay, to create our Max for Live device, we'll go to Max for Live. We're going to make an audio effect. So we'll go ahead here, drag this onto the track, and Max for Live will start up, and we can get going. We'll go ahead and click the Edit button, and of course that'll launch Max. I already have Max running in the background, so it popped up real quick. Here's our basic effect as it is right now, which just passes the input to the output. For our effect, we're going to implement it using the PFFT object. So I'll go ahead now, we're going to make a PFFT, and then we know that the first argument is a name of a patcher. So to add a patcher that is a dependency of this Max for Live device, we'll need to do that using the project manager. So I'll come down here, this little button here will show us our project, and we'll add a new file. We'll call our new file multiband PFFT, and then this patcher, since it will be loaded in a PFFT, we know we're going to need an FFT in, and we have to give it an inlet number. It'll be 1. And we're going to need an FFT out. At the moment, we don't know what we're going to do in here, so we'll just make this a pass-through, like so. We can go ahead and save it, close that window, and now over here in our Max for Live device, we can use that patcher in the PFFT. So go ahead and type it in, multiband PFFT. Okay. We want to create a stereo effect, so that means we're going to need 2 copies of this. So we'll have a left channel and a right channel. And then we can connect them up like so. We don't really want to see all this. This isn't going to make a very nice interface. So I'm going to move it out of the way, and then we can think about what our interface might be. One nice thing that we could do in terms of an interface to a spectral processor is show what the spectrum looks like when it comes in and the spectrum looks like on the output. And we could do that with the plot object as we've seen in the past, but there's another object in Max that's super easy to use and will do an additional feature. That's called the spectroscope. So the spectroscope in its normal working form will show you a spectrum like the plot object does. So if I say I have a saw oscillator at 1000 Hertz and I hook it up, we'll see the spectrum of that. And that's fine. I usually use the plot object myself for that, but there's an additional mode if we look in the inspector, and we can switch this from showing a spectrogram to showing a sonogram. And what this sonogram is showing is it's showing the spectrum on the y-axis based on how dark these colors are, and then it shows the history of it across the x-axis over time. I like to use colors for these, so there's another option in here where I can tell it to operate in color mode. Okay, and I also prefer it drawing the other way, so that's going to be reverse draw, I believe. We can always tweak those settings later. So we can take the plug in, and since this is a stereo effect, but I really don't want to have two of these in here, I'm going to sum the inputs, and then we'll display the summed input here. We can shrink this guy down. We'll make it something like that. And then we can do the same thing for the output. Right now there's no audio coming in or going out, so that just shows black. We'll go ahead and save our device. We're going to call this multiband delay. Okay. Now we can see over here in live, it's loaded it. It shows our two sonograms. If we switch back over here, I'm going to go ahead and switch these to being the scroll instead of draw. Okay. So that gives us a nice way to visualize what's going on, and it looks pretty, and that's all great. We'll go ahead and hide these patch cords. And then we can get on to what we're going to do with this plugin. As I'd mentioned before, we're going to process each of these bands individually, and each of these individual bands is going to have a delay and a feedback. So even if we use a small FFT, let's say for example, we come down here and we say that we want our FFT size to be 128, which is a relatively small FFT, that means we're going to have 64 sliders for feedback and 64 sliders for the delay amount. That's because, remember, we're only going to process half of the frames. If I look at the assistance here, full spectrum flag, we've left that off. We're only going to process half of the frames because we're not processing the mirror image. So that means we have 64 of each. That's a lot of sliders and a lot of stuff to try and cram into here. So one handy way we can do that is we can set up a multi-slider as our interface. The multi-slider object looks like this. I'll put it in horizontal mode, and then I'm going to say that we want this slider. We need to say parameter mode enable, because that will allow the parameters to be stored with our live session. Then we're going to tell it that we want 64 sliders. Further, I find it easier to tell what's going on with these if I change it from the thin line display to a bar display. And then to match sort of a Max for Live aesthetic, I'm going to go ahead and change the slider color to be kind of orangey. Okay. And then if we make it the same height as our sonogram, we can actually have three of these. We could have an input gain, we can have a feedback amount, and then we can have the delay amount. Something like that. I'll go ahead and comment them. So this will be our gain. The gain could act like a filter on the front end. You could imagine, for example, if we turn the feedback all the way up and cut the gain down, then we could just loop one particular band of audio while something else is happening on the other bands. So in the middle here, we're going to have the amount of delay. And then finally over here, we'll have an amount of feedback. These don't all use the same range, so we should go ahead and set ranges for these sliders, and we'll do that down here. Minimum, maximum of the gain, 0 will be the minimum, we could say that we'd make the maximum 2 so that we can boost the signal if we want to on the input. The delay sensible range is going to be between 0 and we could make it 3 seconds. For now, I'm just going to make it 1 second so that we're using less memory, which I'll talk about in just a second. And then the feedback amount, 0 to 1. We definitely don't want to go over 1 with that. Okay, go ahead and save it. So we have our UI now. We can imagine, oh, somehow I lost my sliders. I want these all to be 64 sliders. Okay, now you can see we could draw 64 sliders representing all the gains, one representing all the delay times, and one representing all the feedback amounts. Now that we have our UI and the basic idea of what's going to happen, we actually get to implement it. And to implement it, we'll need to send all of these values into our PFFT so that we can do the processing. One thing about these sliders is they start with slider 0 at the top, and it goes all the way on up to slider number 63 at the bottom. Our spectral bins, the way they're displayed in these two sonograms, are reversed from that. The low frequencies, which would be like bin 0, 1, 2, 3, are at the bottom, all the way on up to the higher bins at the top. So in order to have these oriented the same way, we want 0 to be at the bottom and 127 or 63 up here at the top. So to do that, I'll go ahead and use ZL rev object, which will reverse the order of this list. And we're going to need to do that for all of these. Okay, and then we'll need to send that into our PFFT object. So we can open the PFFT object, hit modify read only, unlock it, and then we can start adding all of our inlets that we need. To do that, we'll use the in objects, just like we would in Poly. We'll have in 2, in 3, and in 4. And if we look at those, we can come up here, and I'm going to put a comment in here so that I remember what they are. Which is going to be gain, delay, and feedback. Now you might be wondering, how in this domain are we going to process all these bands? If we think back to the Forbidden Planet example that we used in a couple of these tutorials, we processed each band by taking the one sample in each FFT frame and modifying it somehow. But here we have 64 samples representing 64 bands, and we want to delay each one of those samples independently from every other sample. So we can't just stick a tap in and tap out object here. We need 64 in this case, or if the FFT size changed, we would need a different number of those. So the answer to that question is that we can use the poly object. And so poly object also takes a patcher, and so now we need to create a patcher that we can load into poly. We'll go back to our project management window, click the plus button again, we'll add another new file. And this time our new file we can name multiband voice. Okay, so here it is. In Poly world, we have an in tilde object, which represents our first input. So we can have that, and we're going to have a similar out object, which represents our first output. So what inputs and outputs are we going to need? Well, if we look back over here at our FFT, we know that we have a real input, we have our imaginary input, And then the FFT-in also provides a bin index so that we know which band in the FFT we're processing. Then we'll also need to know the gain, the delay, and the feedback. So let's go ahead and we'll make inlets for all of those things right now. And I'll say in one, we'll just make a bunch of copies here and then we'll modify them as we need. So these first three are all signals, and those are going to be the real, the imaginary, then we're going to have the frame or the bin index or band number, however you wish to say it. Then this next we'll change this. This is going to be just a control rate number, not a signal. So we'll use the in object with no tilde. And this one is going to be the gain. Then after the gain, we will have the delay. Then after the delay, we will have the feedback. And then after that, we'll have one more thing we're going to need to know. And the thing we're going to need to know in this case is we're going to need to know the frame count, or in other words, how many frames are in our spectrum. The PFFT, because it's 128 sized FFT, that's going to be 64 frames that we're processing at a time. On the output end, we're going to have a real output, and we're also going to have an imaginary output. So we've just put in the inlets and outlets. We'll go ahead and save it. We can come over here to Poly and tell it the name of our patcher, which if we forgot, it's over here in the Project Manager window. This is going to be the multi-band voice. The number of voices, I'm not going to specify right now, because that number of voices will be different depending on the size of the FFT. So, and we want this to work for whatever size we specify. I am, however, going to specify an attribute here called parallel. What the parallel attribute does is it allows Poly to process each voice in a different thread, or a group of voices in a different thread, and in that way it will make use of a multi-core processor to speed everything up. What we're doing in this multi-band processing can use an incredible amount of computational resources on your computer, depending on the size of your FFTs and how many FFTs you're running. So we'll go ahead and say parallel 1 to help manage that. Then we can go ahead and slot in this Poly. I option drag to select both patch cords, and then I can move both at the same time up there. We'll hook these guys up here. And then we have our gain, our delay, and our feedback. Oh, I hooked those up wrong. Go ahead and scoot them over one. We need to hook up our bin number right there. I had mentioned that this is going to be the number of frames in the FFT, and the way that we get that information is with this special object called FFT info, which can be loaded inside of a PFFT patcher. And if I hook this up with a number, it shows us we've got 64 frames in our spectrum. This is the spectrum frame size. This one is the FFT frame size, and you'll see, just as I've explained, the spectrum without the mirror is half the size. So we'll go ahead and we can hook that up. It's not quite that simple though. We need this number to do a couple of things. One is we need this to set the number of voices for the Poly. And that's actually the first thing we needed to do. Since we need to rely on the order that things happen in, we'll use a trigger object to make sure that there's no mistaking what's happening. So I'm going to go ahead, just make the trigger with 3 integers, and we know the very first thing that's going to happen is we're going to send voices $1. So this will set the poly, in this case, to have 64 voices. If we change the size of the FFT, it'll change the number of voices. Then the second thing we want to do here is we need to send this number to our poly voices, but we need to send this number to all of the poly voices. So what we'll do, I'll in fact change the middle trigger here to a bang, and we'll say target 0. Target 0 will tell poly that the next message it receives needs to go to every voice. We can just hook it up here to the same inlet that we're going to send the message into, and then we'll send the 64 in to that inlet, and it will go to every voice through that inlet. So now it's time to start implementing the processing for each band of the FFT. Again, modify read only and unlock it. We know that we want to apply gain, and to apply gain is a simple function of multiplying the real and the imaginary by a certain amount. In fact, right now would be a good time. We'll just test out this very simple processing of modifying the gain. This will be analogous to what we did with the Forbidden Planet example, except we're using the poly to process each band. So what we're going to do then is take the gain, which is going to be a list of 64 numbers coming from the multi-slider, and we need to select just the number for this voice. So to do that, we can go ahead and we can use another ZL object, which will be the ZL.nth. And what ZL.nth will do is it'll choose the nth item from this list. And we can use an object called thisPoly, which will tell us what number voice this current voice is. So it'll look just like that. And then this number, pop out down here, and this will apply our gain. So that is splendid. However, it's actually not quite this simple. Right now, if we think about it, we'll have 64 voices all doing this effects processing. And all 64 voices are getting all of the samples for the real and the imaginary. We want this gain only applied to the one sample that represents the one band of frequencies that we want to process. So we need to select that band up here, and we'll do that again using thisPoly so that we know which band it is, and we'll check the frame number from the FFT. So this is going to say if the frame number of the FFT is the same as the voice number from thisPoly, then this will output a 1. Otherwise it'll output a 0. So if we do a multiply up here, like so, this basically becomes a gate that opens only for the one sample in each spectral frame, which is the sample that we want to process in this poly instance. So having patched that all together, let's see if it's actually going to work or if we missed something along the way. So I saved that voice. Go ahead and save my multiband PFFT. Go ahead and save this. Okay, and then we'll start up our drum loop. Okay, we hear nothing. That's good, because this gain will not, though it shows something here, this isn't actually connected. Our PFFTs need to be reinitialized so that they give us the inlet so we can connect those. Okay, so here is our gain, our delay, which doesn't do anything at the moment, and the feedback, which also doesn't do anything at the moment. Okay, so we did something wrong. So if we come in here, lock this now, and I'm going to put in a couple of messages and some other messages. So here's one. One is what we're all looking at. Voice 2. Okay, so this poly in voice 2, that's not set to the right number. That's because we needed to set a load bank to this poly for that number to have been initialized. So I'll save that. Save that. Come back here. Okay. This is much better. Now if I let a band through here, we can see that this is working a lot like the Forbidden Planet. I put a gain on these bands, and these bands are getting through just like we want to. And if I wanted to filter this somehow, I can use this as a fancy kind of filter. One thing that's happening is that as I'm drawing, it's not modifying. But we can make it continually modify if we take these sliders and click the continuous data output box. Pretty neat, just as it is. And we haven't added the delay yet even. Okay, we'll go ahead and save that. So next up, we'll jump in, go into our poly, say modify read only, and unlock. And now it's time to add our delay. So we can go ahead and add in our tap in object. And remember we said we're going to do a 1 second delay for now, just to keep the requirements of this object to a minimum. And the reason for that is this. We've said that we have 64 bands that we're processing. So that means that the poly contains 64 voices. But remember that we're doing, by default, PFFT is going to give us 2 overlapped FFTs, which means that actually we have 2 copies of everything, which means we're doing 64 times 2 for one of our PFFTs. So that means we're doing 128 voices. And this is a stereo effect. So in fact, we have 256 voices. So our 1 second delay here, we actually have 256 of these 1 second delays. So that's why we enabled the parallel processing over here. If we did 4 overlaps, then we're going to double that. And if we increase the size of our FFT, it's going to also start increasing that number. So that's why we want to play it conservative here a little bit. So now we'll go ahead. Our gain stage is going to be first. That's feeding the whole thing. Then the gain stage is going to go into a tap in and tap out, and we're going to delay both the real and the imaginary amounts. Like so. And then we're going to need feedback for both of these. So we can do our feedback. With a multiply object. So that'll take care of that. Now we need to hook up our feedback amount. I like to put a number box in there in case we need to debug it. And also remember, we need to do the same ZL_nth to get the proper number out of that list that the user interface is providing us. So we can do that for our feedback. And we'll do the same ZL_nth trick. Oops. Also for the delay. Resize some of these comment boxes so they don't interfere with each other. So we can hook up the delay directly to the tap out. There's going to be a problem with it, but I'll hook it up anyway, and then we'll come back and address the problem. Save that. Close it. Save this. Close it. Then to make sure that we've reloaded our FFTs, we'll go ahead and just put a little space in there and let it reload. Save this. I'll go ahead and turn down the gains on everything. And we can turn down the delays on everything and turn down the feedback on everything. Just so we're starting with a clean slate. And then we'll hit play. If we want to hear some stuff. Great. Now when I try to delay these bands, what's going to happen? Well, it sounds kind of cool, and maybe we'd want to use an effect like this, but it's not just delaying these bands and making it show up delayed down here in the time domain, but it's actually shoved them all over the place on the frequency domain. So why is that? If we go back into our PFFT and then open up our voice and do modify read only and unlock so that we can edit this. The problem is that we're delaying, but remember in this poly, which is inside of a PFFT, each consecutive sample does not represent the next sample in time. It represents the next frequency band. So if you delay by some arbitrary number of samples, as we're doing with tap in and tap out, your sample is ending up in a different frequency band. If you want it to end up in the same frequency band, but at a different point in time, then you need to quantize your delay to the number of samples that are in each spectral frame. And that is the reason why I put this inlet here for the frame count, because we'll need to implement this quantization. To implement that quantization, we'll take this frame count. I'll go ahead and stick a number box on it so we can see it when we try to debug. We're going to take the delay time, which is right here, and do a bunch of extra work on it. I'll move these down here like this. What we'll do is we can use the milliseconds to samps object to convert this into samples. And we don't want to be, oops. And I'll use an integer box. And then we're going to round that number. And the rounding increment that we're going to use is going to be the frame count. And we can stick another number box, because if this doesn't work exactly correctly, we'll definitely be in here debugging again in a minute. Then I'm going to use a clip object, and I can type in a default of 64, and we'll say 44/100 since it's 1 second is our time. But then I'll use this frame count to change that minimum value based on reality, whatever the outside FFT is using. So then it's after it clips that, then we go ahead and we'll convert back from samps to milliseconds. And that is the number that will feed our delay. So this whole little doohickey right here, you put a little panel around it, send it to the background, and then put a little comment by it, which is going to be quantize delay to frame size number of samples. Okay. Save that, and then we'll go see if it works. That didn't change. We can just close it, and we'll need to reload these patches again. Give it a second. Save this, and hit play. Okay, we'll need this. Okay, there's those. If we delay these, so we can see that the delays are showing up. These lower bands are delayed and these ones are not. If we delay a couple of them longer, we'll see the transients are knocked over here. Now we can have even more fun. We can add some feedback to it. We could come up here, and if we max out the feedback and give this a little bit of a delay, we'll just let the gain through momentarily and then cut it off. Draw a little bit more there. You get the idea. And we can let it fade out into eternity. So there's our basic effect here. It pulls a little bit from a lot of different places and deals with how to do band independent processing. One last thing I'd like to touch on before we leave the day is that it would be extremely rare for me to build an effect like this and just use the FFT output directly. When you use the FFT output directly, you get a lot of artifacts and little watery sounds, and it's pretty obvious what you're doing. So I like to mask that a little bit and sometimes bring a little bit of life back to the sound. That means that I do a lot of EQing, I do a lot of dynamics processing, sometimes before the FFT and certainly after the FFT. And then one other trick is that I like to use the overdrive object from Max. In fact, I like to use two of these overdrive objects. There's also an overdrive object in Jamoma, which is a third-party package, and it has an overdrive object which has some different options, and I like to use those options as well. Sometimes it's more subtle than Max's overdrive. So if I stack up two of these overdrives, it'll help bring back a little bit of the crunch that gets taken away or stripped out of the sound when you are doing this kind of spectral processing. So I will go ahead here and add that in. I try not to overdo it on the amount of overdrive, but by stacking two overdrive objects together, it lets me get a little bit of the sharpness without making the whole signal sound too distorted. So if I do this, the overdrive range, you know, I could make this a parameter actually. New live.dial. That's what I should be doing with it. Oops. And then we can set this up to have the proper range, which the range for overdrive is between 1 and 10. And then I'll typically keep this down in the 2 or 3 option. You can see even just turning it on with this, we can hear this little band of feedback that's still continuing. Go ahead and so you can hear what that sounds like. So it makes a gain change, but it also kind of just brings some of the sharpness back to the sound. So that's one of my tricks. And if you have any tricks, I'd highly encourage you to leave them in the forum or in the comment section for the video, and we can try to compile a list of tricks that people like to use for post-processing after their FFT effects. So thanks for watching, and I hope you have fun patching with this new bag of tricks.